This is Mohammad Obeidat of Group 6 for the Robotics project. And our task is to create a simulation using Robotics Toolbox of a pick and place task for the robot you see in front of you. Now for each group a different robot is assigned. For our group the robot 3 is assigned to us, which can be seen here. Now in order to simulate our robot, first we have to take physical measurements of its parameters. As you can see here, we have constructed a 2D drawing of the robot where we can see, we have wrote down our parameters that we have measured. The length of the height of the base is 6.5 centimeters. The length of this link is 14.5 centimeters. The length of this link is 19.5 centimeters. The length of this link is 5 centimeters, and the length of this link is 4 centimeters. Our task is to pick and place these blocks. Now these blocks have the dimensions 8 centimeter width, length, 1 centimeter width, and 1.5 centimeter height. However, for our gripper, we wanted the gripper to grab the blocks from the center line. As a result, for the purpose of our project, we're using 2 centimeters as the height instead of 1.7 centimeters. Now, before we enter our DH parameters table, first we have to mention our convection. Here, the z-axis is coming out of the screen towards us, out of the link, out of the joint, and the y-axis is going to the left of the plate, and the x-axes are going upwards through the plate in this direction. For the convection of the end effector, the z-axis is coming out of the joint towards the downwards. The x-axis is going out of the gripper towards the left of the screen, and the y-axis is going into the screen towards in this direction. After covering our convection, we have constructed our DH parameters table, as you can see in front of you. However, after some analysis, it turns out this DH parameter table had some inaccuracies and incorrectness. As a result, we have to construct and reanalyze the robot and take further measurements, and we have constructed this correct DH parameters table. You can also see here we have taken physical measurements of the locations of the blocks in the plate. The blocks are arranged in 3 sets of 2s, 2 blocks on top of each other, and in the final position they are arranged in the Jenga-like tower position where 1 block is placed, 1 block is placed, then 1 block is placed here and here, and then another finally on a block placed here and here. 6 blocks in total. Now, after we have completed our DH parameters table, we used forward kinematics to create the homogeneous matrices of the DH parameters table. As you can see here, we constructed the homogeneous matrices for each link using the DH parameters table, and then using symbolic toolbox in MATLAB, we have found out our final T-transformation matrices. Here's the code, and here's the result, the final transformation matrices for our homogeneous matrix. We have also used hand calculations to find the locations, the transformation matrices for the locations of the blocks. Here you can see we have 3 matrices, 1 for each pair, and for each pair only the z-axes are changing because the blocks are placed on top of each other, so only their height is changing. So for blocks 1 and 4, they have the same matrix. For blocks 2 and 5, they have the same matrix, and for blocks 3 and 6, they have the same matrix. Another change is that for each pair, there's different angle. As you can see from the blocks here, the first group 1 and 4 have a 0 angle from the horizontal angle around the z-axis. The second group has a 30 degree angle, and the third group has a 60 degree angle. Now we have also found the transfer T matrices for the final positions of the block. As you can see here, we have 2 different matrices, one for each, one for the blocks 1, 2, 5, and 6, and the other for the blocks 3 and 4. This can be seen here with this arrangement. Blocks 1, 2, 5, and 6 are arranged in this manner, and blocks 3 and 4 are arranged the other perpendicular to them. Now for the matrices, the orientation is the same. However, the location and the position and location for each block is different. As a result, only the position, only the orientation is consistent for the pairs listed here. Now, for the purpose of our calculation, we have also taken what we call a top position above each block. This was to simulate the fact that the robot will first move above the block, then descend to pick the block up, and then ascend before moving to the final position. So in order to simulate this behavior, we have taken what we call a top position, where we have found the T matrices for the robotic arm above each block. It has the same coordinates as each position. However, with the z-axis being different, taken around 10 centimeters height. Now I will leave you with my teammate, Abdullah, who will Abdullah Al-Yamahi, who will discuss the implementation of the coding in our project.
Hello, my name is Abdullah Al-Yamahi, and to continue from what my partner has mentioned, these are after we got the DH parameters and the physical measurements and the T matrices for all the different positions or all the different poses. It was time for the code implementation in order for us to better visualize it on MATLAB. So initially what we did was we defined all the links and the robot in order to get the DH table, the DH parameters table, and in order to get a plot of the robot. Here, as we can see, we plotted it, giving it initial values of or initial Q values of 0 for the initial position. Then here we just defined the angles, as he mentioned, for the different positions of the blocks, in order to ease the input of the transformation matrices. Following that, we inputted all the transformation matrices here, as we can see here. So there are 4 transformation matrices for each block. There is, as we can see here, there is one for the initial, the picking position, and there is initial top position, which is, as my partner mentioned, the top position before going down to pick up the block. And after that, we go back into this position. Then we go into the final top position above the final location of the block, and then we have this T matrix where we get the final placing position for the block. So after we defined all of the T matrices for all the different locations or different positions of the blocks, we used the iKind function in order to get the QIs for every single motion. So after we got the QIs, we need the QIs in order to do the animation. So after we got the QIs, we had to give some initial values and the mask. What the mask basically says is that we're using the first 3 joints, which are represented by the first 3s, and in the rest we're only using 2 joints, which is represented by 101, the last one representing the end effector. So after that, when it came to the animation, we initially attempted to do it using this method by plotting each set of cues for every single position, one after the other. But as we will see now from the simulation, the issue with this method. So as we can see here, the motion is done extremely fast and is very jerky. So we had to change the approach in order to smoothen the motion and in order to give it a longer time interval for the motion. So this is when we developed the other code for the animation. So what we did essentially was we gave it a time of 1 second to move from one set of QIs to the other. And then here we defined a 37 by 5 matrix, which essentially lists all the QIs with each row representing a single motion, starting from the QI from the initial position of the robot up until the final top position throughout the whole motion. Then we defined n as the length of this matrix, which is 37, and then we created a for loop in order to constantly update the trajectory from one point to another. And here we used the trapezoidal approach for the trapezoidal function in the mtraj in order to get the trajectory, and finally we plotted it. However, in the mtraj, what we did here essentially is the first queue, the first row is considered as the first row is considered as the initial position, and the next row is considered as the final position, and that is repeated up until we reach the final block with a timestamp of 1 second for each motion, and that is all. As for the problems faced, as my partner Obeidat has mentioned, initially we had a mistake in our DH parameters where we had to come and correct it. The mistake was basically that the angles that we had were the opposite. Instead of it being negative pi over 2, it was pi over 2. So we solved that, as he mentioned. And following that, another issue we faced was due to the initial conditions in the I-kind function, where the solution for the QIs was not converging. So we had to constantly change our initial conditions in order to get a converging value. And finally is another issue that we faced also due to the initial conditions, which even though the values were converging, but due to the nature of the I-kind function giving us or selecting one out of several outcomes, we were running through singularities in our code due to the initial conditions. So we had to change the initial conditions in order to avoid these singularities and in order to get the final motion. Now I'm going to show you guys the singularities that we had run into due to the error in the initial conditions. Here, as we can see, that it achieves the initial and final pose. However, the path it takes to those initial poses is very strange due to the singularities that we are facing. And after we showed the simulation for the singularities, as I mentioned, we changed the initial conditions to ensure that we are not running into any more singularities in the motion. And as we will see now, the final motion. So it started in the initial position and it began the pick and place motion. And we will see soon that, or as we can see from now, that the end effector is changing. The orientation of the end effector is changing according to the position, as we just saw here, according to the placing position of the final and the picking position of the blocks. And this is the full animation
of this project. First, we have learned how to apply the knowledge learned in the course in realistic application of robotic programming. We have learned how to apply our DH parameters to the measured values of the robot in order to make sense of our robot's geometry. Then we have learned how to derive our homogeneous matrices, and using symbolic MATLAB toolbox to combine these homogeneous matrices into a final homogeneous matrices describing the pose of a robot. Then we have learned how to find the transformation matrices for the positions of the blocks in order to program our robot. Secondly, it greatly expanded our knowledge of path programming, path planning implementation during the project. Path planning was heavily used during this project, particularly learning how the elbow up and elbow down movements of the robot, as well programming and planning the path the robot takes from picking up one block and placing it at the other final position. Thirdly, we have learned to understand the limitations of simulations and the relation to actual applications. During the simulation, if the robot encounters singularities or other problems, it will often create impossible positions and will move in an impossible pose to replicate in real life. Moreover, the robot can sometimes approach a point in space from a position where it's impossible to reach in real life, such as elbow down, where the robot will pick up the block from an elbow down position that's impossible to create in real life. Finally, we have also learned to troubleshoot problems during the code implementation. As mentioned previously, we have learned how to solve our problem of singularities when we encounter them by changing our initial parameters, as well as encountering other problems during the project, such as or inaccuracies during the DH parameters phase, as well as many other problems encountered during our project runtime. We have learned a great deal of skill and finally applied a lot of knowledge learned in this course during this project, and I believe this project is a great learning opportunity.